Hello and welcome everybody on a new edition of Mantis Development Update for our community of ETC. In this edition, we'd like to present to the community the following topics. Myself, David, will speak about the general project update. Dom will give more detailed insight on the project work that has been completed on the last couple of weeks. And then Bogdan and Anastasia will present a demo of a couple of functionalities that they have been implementing in our Mantis client. As a general update, I would like to say that we want to increase the release of our cadence so we can give our community on a more frequent basis the improvements and functionalities we are developing to be able to test them on our Sagano testnet. In order to do so, we have been working on the test automation to decrease our manual testing and give a safety net for our developers to know when we break something. Also, Mantis documentation content has been growing. We have newer how-to documentation. They are on the latest stage of review and they will be published shortly in our Mantis doc section of our product website. And at last, I'd like to speak about the efforts the team has been putting into being able to spin up your own private network, so we are able to test certain big features in an isolated way. This setup later can be used by the dev community to run their own development and testing networks. Handing over to Dom, that will give us more insight about the project.
Thanks, David. Let's get to it. In the past few weeks, we wrapped up quite a few topics. A lot of scenarios were covered in the area of test automation for the wallet application. This mechanism will be used to keep the wallet application consistent over releases. This suite will grow as new features are introduced to the wallet. Blacklisting and branch resolving during fast sync is available on a feature branch. The whole fast sync improvement effort will be merged into develop in the coming weeks. Additional metrics were added to and merged to develop. The easiest way to see them in action is to follow the tutorial section, locally build and run monitoring client in the project's GitHub README. We also invested effort in verifying that the client is a drop-in replacement for other clients in a pooled mining usage scenario. We have some improvements in mind, but the basic mechanics are in place and ready to use. Beyond that, the work on checkpointing still continues. At the moment, we are dealing with inconsistencies in how regular blocks and checkpointing blocks are being handled. In the fast sync area, we are focusing on the ability to download the chain state in parallel. As mentioned, we are working on more scenarios covering wallet functionalities. And part of the effort to make Mantis stable and of high quality is to cover the application with automated test scenarios. Currently, we are working on a suite that will show checkpointing behaving according to specification. Yet another effort in the never-ending reach for quality and stable operation is to work on enabling tests of Mantis with the Ethereum test suite. Historically, this has been in place, but became out of sync with recent code changes. The goal is to have the automatic mechanism that keeps the team and the application honest, that means following the Ethereum specification. To improve the visibility of developed changes, we asked our devs to prepare short demos. First, we'll start with Bogdan. He's showing off the get proof functionality. Take it away.
Okay, let's try to describe this proposal, the get proof feature. Get proof is a way to verify the data of a certain account, and in order to allow this verification outside the client, an additional function is needed, or an API in this case. And this is also the motivation why you can read through this proposal. Getting to the specification, what we have in the payload is data, the address of the account, the address associated with the account, the storage keys, meaning that this is intended for contract accounts, if that makes sense, where the contract data resides basically, and that's the storage root, and the block number, or we can use latest or earliest as we want. What is returning, what we get is some information regarding that account, like the balance, the code hash, known storage hash, the account proof and the storage proof. And this is where we come to the important part of this feature, the account proof and the storage proof, or the proof within the storage proof. Because, well, let's have a small background of what is a proof and what is the data structure that we are using. So we have the modified Patricia tree, and it consists of 4 types of nodes. One is blank and it's an empty node. The other one is an extension node, and it's a key value, but the value is a hash of another node. A branch node, and that's a bit different, 17 elements, 16 hex characters and a value. And what we are actually looking for is the leaf node that has the key value association that we are actually searching here or within this whole object, because this is the account. So the proof consists of a key and the value found at this key and all the nodes, and this is stored in the account proof and in this proof within the storage proof. So we need all the nodes traversed to reach the value. Okay, so the proof shows that the tree has the given value at the end point of a given path. And this is possible, this verification is possible because the hashes of all nodes going up are dependent on one another. Okay, so it can be calculated. Going out, so well, I created a contract account and I have an account here, so we can verify this somehow. So I have an account, I'll copy the account and I'm going to Insomnia to query this API. Okay, so this is basically the externally owned account. So in this case we will not have a storage proof because we don't have data related to a contract. So this is not necessarily useful in this case. So if we send it, I have the client running, of course. We get the result, and the result is actually the account proof. And this is what I was saying earlier, is basically the array of all the hash nodes that are being traversed to find this final value, in this case the account. The balance, and the balance is not empty as you saw it earlier. Code hash, storage hash, and storage proof. In this case, the storage proof is empty, of course. Externally on the account, the key is 0. Okay, if we change, if we put a random key, we will find a random key here. The proof will be empty, of course, because there's nothing there, and the value will be a default value of 0 because no value was found based on this key. Now, what I wanted to show also is basically if we don't find the address and we change a small character here, we receive actually an error, no account found for address in the block number. And this is also the behavior of the other clients, so we don't actually want to return anything if the address is not there. Now it's a bit different for a contract account. And a contract account, I think I have it ready, yeah, the contract address here. This is a transaction that I did earlier. Okay, so if we search for this one, okay, let's see. We do find an account, and again, same behavior. This is the account proof. So it's the array of nodes. The balance, and in this case is 0 because it's a contract account. When I created, I didn't actually set the balance, so by default it's 0. A storage hash and storage proof. Now this is changing here because it's a contract account. It has some data inside the storage root, and based on this key, there's no value, of course, because it's just a random key. Didn't find anything, but the proof is different because the proof will always return something in case of, let's say, a storage proof, because there will, for a contract account, there will always be something there. So in this case, we return the root node. But if we have a key here that actually points to a value that exists inside the storage root, then this proof will be similar to what we see in the account proof, meaning that it will go from the root node all the way down to the leaf node, where we can actually see and query the value expected.
Next is a demo by Anastasia. She's showcasing the ongoing work on the peer discovery algorithm.
Hi guys, my name is Anastasia and I'm a part of the Mantis team. I'm a developer and I wanted to show you something that I've been working on in the past sprint, and it was mainly performance improvements, and in particular it was improving the peer discovery algorithm. So as you know, when the client is up and running, it tries to connect to other nodes and usually discovers lots of them, but not all of them are suitable for connection. So we wanted to improve the successful rate of connections with this feature. And mainly it was done by changing two things, and one is increasing the time we blacklist some of the nodes, and it can be nodes with incompatible protocols or from other networks, and we know for sure that this is not going to be changed in near a couple of hours, so then we know that we can safely blacklist them for some time, at least some hours. So this was one part, and the second part is about first going through the whole list of nodes that we discovered before we retry the ones who failed before. And yeah, that's it. That's what I did, and I wanted to showcase this somehow. And the only thing that I came up with is just to run the nodes, run the Mantis client before the change and after the change. So you can see in the logs how many successful connections were established after the set amount of time. And I pre-recorded this because otherwise we would have to sit here for like 45 minutes waiting for the results, because yeah, that's the time frame that I chose for it. So I'm just gonna present the video I made showcasing that. And here it goes. So on the left is the client before the change, and on the right is after. I was running it both for 45 minutes and checking in the end how many peers were successfully connected out of the peers that were just discovered. And in both cases, discovered nodes were like 4,200, something like that. And successful ones were 4 in a, handshake. There's 4 on the left side and 6 on the right one. And out of the approximately the same amount of discovered nodes, it means 50% improvement in successful connection. So this is the same result as I got while testing the feature, and I ran it like multiple times, 1 hour in 1 hour time frames, and it was approximately the same. It was 55% improvement. So yeah, this is it. That's what I wanted to show you, and my update is over. So I hope to see you next time. Bye bye.
Great stuff. I need to mention here that these improvements are part of an overall effort to have Mantis be quicker at synchronizing and discovering more of the network consistently. That's it from me, David. Back to you.
Thank you, Dom. And remember to join our social media channels for our latest news and updates. You can find the link below on the video description. Until our next dev call, bye.